Okay. Hey, before we get into our new stuff for today, I want to talk about something really quickly. This is going to be important. We'll talk about it more later, but I want to try and make a connection between something that we did last class and something that we've been doing all year, because this is pretty key. I actually talked to Mr. Sweats about this. He's going to be, if you're a junior and you're taking calc next year, he'll be your teacher. If you're a senior and you're taking calc, I'm sure that your professor at the university is going to want you to know this too. All right, so I want us to think about a parent function that we've not dealt with before, but let's think about this function here. You don't need to write this down, just watch. Y equals sine x. That's a parent function. Okay, just like y equals x squared is a parent function and y equals square root of x is a parent function, or y equals log x. Y equals sine x is a parent function. Now, at this point, you guys know what one period of sine looks like. I'm hoping that you're thinking something like that, right? Can you guys tell me what the amplitude of our parent function would be? It would be 1 because there's a 1 out in front of here, right? And can you tell me what the period of my parent function would be? What's omega? What is omega first? Omega is the one that appears in the equation. It's not actually written down, but what is the invisible number in front of the x? Omega is 1, which means that the period is 2 pi times the reciprocal of 1, aka the period is 2 pi. Okay? So, is this shocking to you that our regular parent function has a period of 2 pi? 2 pi is once all the way around the circle. This is related to that, right? So that's how wide one period of a sine function is, if we're talking just plain old sine x, okay? Now, what happens when I start doing stuff like this? If I say instead of y equals sine x, it's y equals 3 sine of, let's just say, pi over 4x. I want you guys thinking back to chapter 1, like the 3rd week of pre-calculus, way back in the fall. What kind of transformation is going to be happening because of this 3 that's being multiplied on the outside of my function? That's going to be a stretch, vertical or horizontal stretch. This is a vertical stretch by how much? By 3. So which means my amplitude is no longer going to be 1. My amplitude is now going to be 3. So does it kind of make sense what's going on there? Like our amplitude just got stretched vertically, like in the sense of transformations. Now, here's where this gets a little bit weird, but don't miss this, okay? This pi over 4, we've been calling it omega, and it is omega. But in terms of transformations, what does this do to our function? It says a horizontal. And is it a stretch or a compression? Horizontal. Now, when we think about things being multiplied on the inside, we think of them being multiplied by their reciprocals, right? If it had said, for example, sine of 3x, this would be a horizontal compression by 1 over 3, right? So this is going to be a horizontal stretch by 4 over pi. Just kind of yucky. But wait, this is where I really hope you're going to make the connection. What was my original period? 2 pi. If I wanted to stretch 2 pi by a factor of 4 over pi, I would take 2 pi and I would multiply it by 4 over pi. So this was my period for my parent function, and then we multiply it by the reciprocal of this number, and that gets me my new period for my stretched out function. Are you seeing what I'm hoping you're seeing here? When did we ever do 2 pi times the reciprocal of that number? That was our formula for t, right? That's why this is like it is, because when we're looking at a number that's being multiplied inside of the function, we actually have to look at that multiplier as being the reciprocal of that. That's what's going to tell us what to multiply for our horizontal stretch or compression. Okay, so because the original one was 2 pi, this is why we've got to do 2 pi times the reciprocal of this. Okay, all right, so this is going to be our new general form of our sinusoid. Sinusoid encompasses both sines and cosines. You'll see why in a second. If you remember on Friday last week, I told you that I was going to hide some information from you and then reveal it today. That's coming up here, okay? So we're generalizing this thing. Not a whole lot's going to change. A is still our amplitude. And omega is still omega, which doesn't really tell us much, but we have that t is equal to 2 pi times the reciprocal of omega, and t is the period. So omega still helps us find our period. What's different in this is that we also have this minus h happening on the inside, and in terms of transformations, what is going to happen when I subtract something on the inside of the function? It's going to shift it horizontally or vertically? Horizontally, and everything's backwards from what we expect, right? So if this had been x minus 2, that would be a shift to the right. And if it had been something like x plus 3, that would be a shift to the left. And we're used to thinking that from our transformations. And then that plus k is happening on the outside. In terms of transformations, what happens when we add or subtract something on the outside of our function? We get a vertical shift. So we're going to be either moving it up or down. Give me an example for something that would move it up. If it was plus 5, we'd be moving up. Give me an example of something that would move it down. Minus 2, minus 3, minus 5. I heard lots of them. Yes. Minus whatever is going to move it down. And if you guys remember when we were talking about some more advanced transformations, I told you that if you can factor something out on the inside so that you just have x plus or minus something, there was a simple rule about what order to do the transformations in. And that rule was do your shifting last. So the only thing that's going to change today, we are still going to use a and omega to figure out how big our little frame is. Okay? So that's our stretching and compressing. The only thing that's going to be different is that our little frame is not always going to be at the origin right here. So what I showed you on Friday was that our origin was always right here. Regardless of whether the graph went through the origin or not, the origin was always right here. Now this frame is just going to move around depending on our shifts. That's it. That's the only new thing for today. Okay? And then there's going to be one other thing that you're going to see, and you're going to be like, okay, that's the piece that he kind of hid from us before. So let's do our first example here, and you guys will have your little aha moment here. Pull back the curtain. All right, so I think it is a good idea, and I told you this on Friday, when you're doing these problems to start off, I think it's a really good idea to just make a quick sketch of what your kind of general waveform is going to look like. Some of you will see why I encourage you to do this. This is a positive cosine. Can you guys remember where the points go for a positive cosine? Does it go through the origin or a max or a min? Max, and then comes down. And it's going to have kind of a U-shaped . All right, what is this 2 out front going to tell us about that thing? That tells us that our amplitude, that tells us that that distance is 2 and this distance is 2. So our parent cosine has been stretched vertically by a factor of 2. And then we've got omega sitting right here, but what we really want is t. That'll tell us how wide to make this thing. So let's figure out how wide we're going to stretch it. So t is equal to 2 pi times the reciprocal omega, same as what we did on Friday. 2 pi times 2 over pi. Pi's will cancel. That'll just become 4. That tells us that t is 4. So our parent function is 2 pi. We've stretched it out to 4. Actually, that would be a compression, wouldn't it? 2 pi is bigger than 4. At any rate, we've changed how wide it is. It is now 4. Now, the only thing that we have left to do is shift it. And this minus 1 is going to be a shift to the left or a shift to the right? Shift to the right. So we're going to shift right by 1. So last Friday, every time we built our box, we always built it off of the origin. We're not going to build it off the origin. We're going to build it off an anchor point that's been shifted to the right by 1 point. We're going to build it off of this point. So from here, we'll go up by 2 and down by 2. And we'll draw a box that is 4 units wide. Freshman. Calling it. No offense to any freshmen in the room. I don't think we have any freshmen in Precalc this year. All right, so let's get our cosine on there. So far so good, guys. Are we feeling okay? Like all we've done is we've just shifted things around. Okay, and we did our shift at the end because we'd chosen the size of the box ahead of time. So here we go. I'm going to put these points on here, and then we just have to do that super tedious piece where we go back and we count and put all the points on there. And then I like to do my x-intercepts first because, I don't know, it just goes faster for me. And then I kind of do in between those for my maxes and mins. We connect them up and we're good to go. We'll grab our calculators and check this in a minute. But at some point here in the next minute where I'm hoping I'm going to get an interesting question, or maybe I can hear a couple people realizing some things already. If you think about what is the little kind of fib that I told you on Friday. I think I may have told you already, or at least spoiler hinted at it a little bit. On Friday, if I had asked you what type of graph this was, would you have said sine or cosine? That's a positive sine graph, right? But it's not actually. It's a cosine graph. And so here's the piece that I kind of danced around. I didn't purposely try and mislead you. I was just trying to simplify things so that we can kind of wrap our heads around the basics. But there actually is no such thing as a sine versus a cosine graph. They are all the same thing. They're all just shifted versions of each other. The fact is that I could write an equation for this as a cosine equation or a sine equation or a negative cosine equation or a negative sine equation. They would all have different shifts, but I could write it. So there are infinitely many different ways to write the equation for this using sines, cosines, positives, and negatives. And we're going to practice that in a little bit. So that's kind of the big thing. I kind of led you to believe that there was a difference between a sine and a cosine. In terms of picking out one general waveform of it, this is still valuable to us though, because that's how we're going to be identifying where our waveform starts and ends, which is going to tell us what our shift is going to be. So let's practice this a little bit more. See if you can do as much of number 2 as you can. If you would, I would highly recommend that you start by sketching yourself a little window pane here, making a sketch of what a period of, air quotes this time, negative sine looks like. Bless you. And what do we know about the size of this thing? At this point, we know how far up and how far down it goes. And we have enough information to find, with a little bit of work, how wide it is. At some point, you're going to have to ask yourself the question, are we shifting to the left or to the right for this one? Put that phone away, come on. Put it away. Hopefully you're recognizing we need to shift to the left by 2, so instead of starting our frame at the origin, we're going to take the origin and move it to the left by 2. And then from there, go up and down by 3. And then over 8, I went too far. So that's our full period. We'll chop it up into those kind of 4 or 8 segments to find our key points. Oh, we can deal. And then just the tedious part of filling in the rest of the graph. Once you get that graphed, if you would please get your graphing calculator out. Let's plug it in and make sure that that it's working out. Start with your window. My window is all kinds of messed up. We need to go from -10 to 10 by 1s, and y goes from -4 to 4. If you weren't here on Friday, I showed you how to set up your grid. You might ask a buddy to show you that. And I'm feeling pretty confident. All right, what questions do you guys have at this point? Is this feeling okay so far? Same thing we were doing Friday, we're just moving the box around, right? All right, there are some other kind of tricky things that are going to happen here. One of those we're going to get into next. Let's ask a question here if we need to. We good to go? All right, here we go. This equation looks different from the last two. Can you spot the difference? Yeah, so what's different is it's not in this format where the x is isolated from omega by a parenthesis. And we want that. Otherwise, things get really complicated. I could accomplish this with transformations. I would have to do my shift first, and then I would have to do my horizontal stretch or compression, which would also change how far I'm shifting, which is going to be kind of annoying. So this will be much easier if we can force it into the format that's a little bit more friendly to us. So we're going to do that. We're just going to factor this pi over 4 out on the inside. Now, it's at this point that some of my students start freaking out because they realize they're going to have to deal with some fractions here. But let me remind you that you learned back in 6th grade how to multiply and divide fractions. 6th or 7th grade, maybe even before that. I don't know. Correct me if I'm wrong. When we factor something out, we are dividing. Right? That's how we factor something out. If, for example, I gave you 2x plus 10 and asked you to factor a 2 out, you all know what you would be in there with the x. It'd be a 5, right? Why is it a 5? Because 10 divided by 2 is 5. So right now, and you might need to actually write this down, but take this 3 pi over 2 and divide it by the thing that we're factoring out. Divide it by pi over 4. Do you remember the trick for dividing fractions? KFC or KCF? Keep, change, flip. My teacher used to say, just flip and multiply. Flip the second one and change it into multiplication. 3 pi over 2 times 4 over pi. And if we can't do that in our heads, then let's find a different place to be. Pi's cancel. 12 over 2 is 6. As long as you're getting a 6, that's fine. All right. So we're going to graph this thing now, and this time around, are you going to be shifting left or right? Left by 6. So we'll be shifting left by 6. So I'm going to build my box off of this anchor point right here. And I know that my box is going to go up and down by 3. So I'm skipping the part where I do my little sketch. And I just need to know how wide to make my box. So let's figure out what t is. 2 pi times the reciprocal of pi over 4, I believe is going to be 8. So this work up here is happening because I needed to factor a pi over 4 out of this thing. And when we factor something out, we're dividing it. So to figure out what this turns into, I need to divide it by the thing that I'm factoring out. And remember, dividing by a fraction is the same as multiplying by its reciprocal. And what do we got? Positive sign here. Someone pointed out that these should have arrows on them. I usually don't draw the arrows because it makes you think that they should be going up forever and ever. In this context, it means it would repeat forever and ever. So here's our big reveal for today. On Friday, I would have asked you, what kind of equation is this? And on Friday, you probably would have told me this is a negative cosine. And the truth is that it is a negative cosine, but it's also a sine. And it's also a positive cosine. And it's a negative sign. So we're not going to graph, I'm not going to go through and graph number 4, but can you guys at least take the time to get it into the friendly formats? It's going to look like this. Yes. Problem 3 and problem 2, yeah, they do. I never noticed that. Good eye, look at that. Problem 3 and problem 2, the graph is exactly the same, but the equations are different. Whoa. Whoa. Folks, I'm interested in right now just you figuring out what's going to go in here. It's going to be minus something. What would I multiply pi over 2 by to get 3 pi? Or 3 pi divided by pi over 2, same thing as 3 pi times 2 over pi. That's kind of boring. 6 again. All right, we're going to be moving on unless anybody has any questions. So far we've just been shifting left and right. Sometimes we have to do a little factoring, which might cause us to have to do a little bit of fraction work off to the side, but you can handle it. I believe in you. All right, see if we can go the opposite direction. Right. Example 5 here. So I am establishing in this example that I want us to write a negative sign equation. So for this one, I'm looking for you to write a negative sign equation. Just to remind you what a negative sign looks like, it's going to go through the origin and then down and then back up. Sort of that S shape, but it's going down first. So what I would like you to do is scan through this wobbly looking waveform and find me where does a negative sign start and where does a negative sign end. Can someone give me an X value where a negative sign starts? I got a negative sign starting here at 1. How far to the right does it go? It goes out to 9. So there is a negative sign. If you could go ahead and draw a box around that, it'd be helpful to us in just a moment. Were there any other options? Yeah, give me another place where a negative sign starts. -7, I see a negative sign starting here, and where does it end? Oh, it ends at 1. It's strange how one starts in the same place that another one ends, or is that? So we can't see it on the graph, but you're claiming that we're going to have another one that starts over here at -15? And then there's another one that would start here at 9 and go to 17. So there's lots of them here. Let's write an equation. What's going to be the same about all of these, no matter which one we pick? What's going to be the same about all of them? Amplitude's the same for each of them. The amplitude is 3 for all of them. Agreed? So let's go ahead and put a 3 out in front here. What else is going to be the same for each of these? Omega is going to be the same because the period's the same for all of them. T is 8 no matter which one we're picking, right? So what's omega going to be? 2 pi times 1 over 8 is 2 pi over 8, pi over 4. So omega is pi over 4. Now, if I pick this one that I just boxed in blue, that would be a shift to the right by 1. What would go inside my parentheses for a shift to the right by 1? -1. The only thing that would change if I had picked this one that I boxed in red here is that x minus 1 would change. This one has been shifted to the left by 7. What would that be instead? +7. And for this green one that we said wasn't on our graph, but we were pretty certain that it would start at -15, this would be a +15. And by the way, we said there was another one that was starting here at 9. That would be shifted to the right by 9, so that would be a -9. What's going on here? What's the relationship? +8, +8, +8, +8. And the significance of 8 is that is our period. That's one time all the way around the circle. This is kind of like our coterminal angles, right? So if I wanted you to write 15 different equations for this thing, would you be able to do it? Yeah, you would just keep changing these numbers and keep adding or subtracting 8 from them. If you guys could you get your calculators out? We've already set up our window for this. I want you to type in these 4 equations. I wish there was a way to copy and paste. I have not figured that out on these calculators yet. I want you to type in all 4 of them, and we're going to graph them all at once. And what I'm hoping that we'll see is that they all overlap each other. Mine's going to graph them one after another. Here comes another one, right over top. If you've got the black and white version of the calculator, after you see the first one graph, it's just going to look like it's sitting there doing nothing because it's just drawing right over top of the original. And if not, you might have typed something in incorrectly. So, here's my challenge to you. And I'm not going to give you answers to these because there are an infinite number of answers, but see if you can rise to the challenge here. Can you write me 4 different equations? I would like you to write me one that has a positive sign, one with a negative sign, one with a positive cosine, and one with a negative cosine that all have this same graph. And I'm not going to give you answers because, again, there are lots and lots of them. So what I'd like you to do once you get them written is type them all into your calculator and make sure you're getting the same graph for all 4 of them. So I'm going to give you a few minutes to do this. This takes a little while. But see if you can find me one of each of those in this graph. Write me 4 different equations for this thing. Keep in mind that there are 2 of these 3 numbers that are going to be the same in all 4 of them. What's going to be the same in all 4? Amplitude is going to be the same, and the period, which means omega, is going to be the same. So once you figure out an amplitude and omega, you can go ahead and fill that in for all 4 of your equations. The only thing that's going to change will be your horizontal shifts. Give that a shot. We'll come back together here in a couple of minutes and move on together. So multitasking as you're finishing up here. On Friday last week, I encouraged everybody to create a small sketch of what their period was going to look like before they did the actual one, and a lot of you probably were like, I'm not going to waste the time to do that. My reason for that is some people find it really easy to look at a graph like this and pull out a sine or a negative sign or a cosine or a negative cosine. For some people, that's like not easy, and I don't want anybody thinking like they're less than because it's not jumping out at them. It's tough for some people. If you are finding it tough to look at this and find a negative where a negative cosine starts and ends, one thing that may help you with that is when you're doing these types of problems, make this little sketch. The other thing that I have students, I've had some success with students in the past is mask it. So if you're looking for a positive sign, you know that a positive sign is going to start where your graph is at the x-axis moving upwards. So use like a note card or the edge of a piece of paper to mask off the rest of it. And then do the same thing on the flip side. I know a negative sign is going to end, or a positive sign is going to end when we get back to the x-axis like this. And that makes it easier to see, oh, okay, my period's 4, and I've got a positive sign that starts at -6 has been shifted to the left by 6. Should make this a -6, that would make this a +6. That is not the only one for a positive sign. There's lots of them on here. The Chapter 4 test is the most annoying test to grade all year because there are an infinite number of correct answers to all the problems. So I can't just like look at it and be like, that's right, that's not right. I got to actually like look at your answer and work it out and make sure it works. You could do that, but then you got to keep in mind I'm also the guy that's setting the adjustment on the tests. And you know, there's like a psychology to the whole thing too. But yes, you could. If you wanted to be really, really mean, you could take this 6 and you could add any multiple of, what was our period? You could add any multiple of 4 to it. So you could say, I'm going to do 6 plus 723 times 4. Mr. Height, my answer is x plus 17,352. And then I would have to go back and figure out, is that... I don't think you can make these decimals on this one, but some of the other ones you could. Yeah. All right. So we haven't done any with vertical shifts yet, but we're about to. Do you think this is going to make things all that much more difficult? No. In fact, I'll show you, and I'll give you this one hint that's going to make things way easier for you if you kind of get in the habit of doing this. Very first thing when I do a problem with a vertical shift is I'm going to take that +2, and I'm going to draw a horizontal line where my new, and I'm doing an air quote here, where my new x-axis was. So everything's been shifted up by 2. My x-axis used to be down there. Now my x-axis is here. Can I get you guys to draw that horizontal line for me? And then use your amplitude to go ahead and draw a line for your maxes. So up by 3, and your mins. Down by 3. This makes things so much easier. Then when you go to draw your points, all of your points are going to be on one of those 3 lines. All right, so I'm going to sketch my positive sign. We know it's going to go up by 3 and down by 3. We already got that. My really key piece of information is how wide is it going to be? What's the period? That's omega. Period is 2 pi times the reciprocal of that, aka 6. And which direction are we shifting this time? We're shifting the right by 5. Are we going to have room to do this whole period on here? All right. I'm hearing some good strategies here. So if we're shifting to the right by 5, this is where the period's going to start, right? So some people are just adding an extra box at the end here, but I'm hearing another one. You said you did it behind it, and I'm assuming you mean instead of drawing the period that starts right here, you're drawing the period that comes before it, yeah. Which we know there's going to be an identical one over here too. So it has been shifted to the right by 5, but I know there's an identical period going to the left from there that ends at that same point. So we could draw this one instead and chop this one up and use that as our reference. Whatever one works better for you. We've got some of those in-betweener points for these. Some of us are more flexible with those than others. I'm not hearing any deep sighs, so. Anything's possible. Now, most of these that you're going to do for practice are ones that I'm going to make, and I don't usually do that. The question is, are we ever going to have an amplitude that's got a decimal, and then also like important points that are going to fall in between lattice points? We could. All right, we're going to skip number 8 in the interest of time here. If you've already done it, that's great practice. Good for you. If you have done number 8, if anybody was working ahead on number 8, your first order of business would be to factor out that pi over 4. You should have gotten x, what multiplies by pi over 4 to get pi over 2? 2 pi? Just 2. Thank you. I'm getting ahead of myself. All right, flip over. We're going to streamline this a little bit. We're just going to write one equation here. But I'm gonna give you another big hint. Well, it's actually the same one. Draw me 3 horizontal lines on this graph. Before you do anything else, draw me 3 horizontal lines on this graph. This is going to make this easier for you to see. Draw one that goes through the max and one that goes through the min. And then one that goes halfway between those. Folks, do you know a mathematical operation that will tell you a number that's exactly halfway between 2 other numbers? To add them together and divide by 2, otherwise known as take the average of the 2 numbers. -2 and +6, add those together, I get 4, divided by 2 is 2. We're almost there. We're almost there. Let's do a, I don't know, let's do a positive sign. Can you spot a positive sign on there someplace? I'm going for the one that's kind of on either side of the y-axis. Do you see the one I'm talking about? Starts here and ends here. And what do I see? I got a period of 1, 2, 3, 4, 5, 6, 7, 8. An amplitude of 4. This 2 right here is a vertical shift. We also have a horizontal shift to the left by 3. And we're going to need an omega. And then we just got to put it all together. Any questions on number 9? If you were doing this in your assignment, what would you do immediately after writing that equation? You would plug it in and graph it. And I'll tell you, when I'm checking these, actually I'll show you this in a minute when we check the next one. When I'm checking these, I would also graph my 3 horizontal lines. It makes it easier for me to check it visually. We're skipping 10 and moving on to 11. All right, this is not in the correct form. Well, there's no such thing as a correct form. It's not in the friendliest of forms, so let's factor this 2 out. This one's a little bit easier. I just need to take 3 pi and divide it by 2. 3 pi over 2. All right, let's start with our horizontal lines. Let's draw those 3 horizontal lines first. So we know we've got a downshift by 5, so my new x-axis is going to happen at -5. And the amplitude's 2, so we'll go up by 2 and down by 2 from there. I know my horizontal shift, but I don't have my period yet, so I probably need to do that here. So T is 2 pi times the reciprocal of omega. Omega is 2, so 2 pi times a half, which is pi. Ooh. So my period is pi. And is my shift left by 3 pi over 2 or right by 3 pi over 2? Left. So I need to start at negative 3 pi over 2. And then I need to go over by pi, which is going to be where? What's negative 3 pi over 2 plus pi? It's negative pi over 2. We're going to have some fraction stuff to deal with. This is kind of one of those annoying ones because we're going to have, we got to fit a full period in that little tiny space there. I know. It's fine though. It's fine because if you do your x-intercepts first, air quote x-intercepts, this is going to go way faster. It looks like my x-intercepts, my shifted x-intercepts are just in the middle in between each of my tick marks. And then my maxes and mins happen on every other tick mark. So what do you guys think? Do you like these ones with the x-axis in terms of pi, or would you rather have integers? Me too. Either are fine. We've got to think a little bit more for these ones, but
I honestly don't care as long as you don't make us do such small periods.
Before we move on here, I want to make sure we're good on checking these. So I would like you to graph this, but you do need to reset your window before you graph it. When you're setting your x max and your x min, you're going to be putting stuff in terms of pi, and that's fine. Your calculator has a pi button on it. So for x min, type in negative 3 pi, and don't be freaked out if you take your cursor off of that and it changes into a decimal for you. You're going to type in negative 3 pi, and as soon as you move down to x max, it's going to change it to negative 9 point something. So there's negative 3 pi. Here's positive 3 pi. And then this is key. How big is my x scale? You can see, where's the first tick mark? The first tick mark happens at pi over 2, right? So my x scale is pi over 2. Type in pi over 2. It's going to change it into a decimal for you. My y values go from negative 8 to positive 8. And then I'm going to go ahead and type in my equation. And when I do this, for these, it helps me to see if I did it correctly if I also type in the 3 horizontal lines. So I'm going to do negative 2 cosine. And I'm just doing the original one, not my modified one, but the original one, just to make sure I didn't make a mistake when I modified it. And then I'm going to graph my 3 horizontal lines. One was at negative 5, one was at negative 3, and one was at negative 7. So negative 5, negative 3, and negative 7. I find that this helps me to check and make sure that my points are in the right place if I have those 3 horizontal lines graphed too. I'm feeling pretty confident about that. We're just going to do one more together, guys. We'll do 13. These are the best. Any questions on 11 before we go to 13? So when we come back on Friday, we're going to be doing applications of sinusoids. So we'll be looking at things like temperature variation over time, number of daylight hours, that kind of stuff. And we're going to have to deal with some things with weird scales, but that's okay. This isn't bad. Can I get you guys to draw your 3 horizontal lines on here for me? It's pretty clear that one of them is at, where's the top one? It's halfway between 2400 and 2800. That's 2600. And the bottom one is at, what's that, 200? So what's the average of 2600 and 200? 2600 plus 200 is 2800 divided by 2 is 1400. The reason I wanted to make sure we went over this is we're going to need to pick a good trig function for this, and we need to choose between sine and cosine, a positive and negative version. And in this particular problem, there is one of those 4 options that is going to work way better than the other 3. Why would I not want to pick cosine? It's really hard for me to see, where this peak is. This would be the start of a cosine period, and it's kind of in between lattice points, somewhere between 0.1 and 0.2, but I don't know how far. Negative cosine kind of has the same problem. Sine looks promising, though. I can see where we're crossing the x-axis here, and then I can see where we're crossing again over here. So I would pick a sine equation for this one over the other ones. And then from here, we just need to do the work to find everything. We're going to need our period. It's going from 0.1 to 0.4, so that would be 0.3. Oh, and this is where we're going to lose some points, some of us. Go ahead and find your omega value for me. And let me just repeat that in this class, we do not include fractions inside of a fraction. That means we do not include decimals inside of a fraction either. If you wrote omega as 2 pi over 0.3, you're going to lose some points. 2 pi over 0.3 is not an acceptable final answer for omega. Simplify that so there are no decimals or fractions inside of your fraction. Now, if you can't do that in your head, which, by the way, is pretty easy, just multiply by 10 on the top and bottom. Right? It would be 20 pi over 3. But if you can't do that in your head, remember your calculator can. Type in 2 divided by 0.3 and math frac it. It's 20 over 3. So please do not use 2 pi over 0.3. Use 20 pi over 3 for omega. You don't like that? Why not? It seems wrong. Well, with some practice, it will seem right. It's just not as simplified as it could be.
But this not simplified version is more easy to understand. Whatever 0.3 looks way worse than 20. Yeah, but that's just close. Like I understand it better if it's the other way.
Well, I'll tell you what. You go get your PhD in your postdoc and become a math professor, and you can let your students do it this way. I'm gonna force you to do it the way that your college professors are probably going to, though. So I'm not gonna force you to do anything. I'm gonna encourage you to by establishing some minor consequences for not doing it this way. You could. My main thing is that I just don't want decimals inside of fractions. Decimals aren't the problem. It's just that decimals are technically fractions. And if you got a fraction inside of a fraction, that can be simplified. Yeah. You certainly can. Hey, I got some good news and some bad news for you. The very back page of your packet, if you look at the very back page of your packet, you're going to see something familiar. We had a little miscommunication when I had my TA copy these things. Hey, haven't you guys already done this? Yeah. So when we copied these, we accidentally... Hey guys, don't miss this. I'm taking work off your plate. If you listen to this, you might, you're welcome to do it again if you want to. This whole back page of the packet is a repeat from the last packet. It should not have been on there. It is not part of your work. You can tear it off, but please don't throw it away. It's got graph paper on the back of it. Save that to use for our applications, which we're going to need on Friday. Your assignment is P1 through P20, and there's some problems out of the textbook just to keep them sharp. Those are listed on Canvas. I'm going to have to check these on Friday.